Alternating current is the most practical and versatile source of power for most electrical and electronic applications. High voltage alternating current can be transmitted over long distances without appreciable loss and readily transformed to low voltages for practical use. AC can also be radiated from an antenna. This capability is responsible for the development of radio communication. All generators produce AC internally. In this basic AC generator, the arms of the loop cut lines of force in opposite directions, causing electromotive force of opposite polarity to be generated in the conductor. To maintain the AC character of the output in this generator, we use slip rings instead of the commutator segments used in the DC generator. This use of slip rings is the only structural difference between AC and DC generators. One complete revolution of the armature will produce one cycle of alternating voltage. If the armature rotates once each second, the frequency of the alternating electromotive force or voltage is 1 cycle per second. 10 mechanical revolutions of the armature per second produce a frequency of 10 cycles per second. Frequency, or the number of cycles per period of time, is directly related to the rotating speed. In this example, the two-pole machine used has one magnetic field. As the armature makes one revolution, one magnetic field is traversed. Adding another pair of poles adds another magnetic field. Now there are two magnetic fields. The armature moves through one field in half a revolution. In one complete revolution of 360 mechanical degrees, the armature passes through two fields equal to 720 electrical degrees, and 2 cycles of AC are generated. Frequency can be changed in the AC generator by the introduction of additional magnetic fields. The relationship between mechanical and electrical degrees depends on the number of poles in the generator field. In a 4-pole field, we saw that 360 mechanical degrees equals 720 electrical degrees, a ratio of 1 to 2. In a 6-pole field, the ratio is 1 to 3, and so forth. The formula for frequency in an AC generator can be expressed as follows. F, which is frequency in cycles per second, equals P, the number of poles, times N, revolutions per minute, over 120. We can find the frequency of a 4-pole AC generator whose speed of rotation is 600 revolutions per minute by substituting 4 for the number of poles, P, and 600, the RPM, for N. Here the frequency is 20 cycles per second. The output of the AC generator may be increased by the addition of loops to the armature. Changing the construction of the armature in this way provides additional outputs. The resultant output here is the algebraic sum of the individual waves. The armature of the practical AC generator is wound with many turns of wire. There are several different types of AC generators, or as they are sometimes called, alternators. This is an elementary single-phase AC generator. The armature of the single-phase AC generator is wound with many turns of wire. These coils are connected in series, so that at any given instant of time, the total voltage induced is the sum of the voltages induced in each individual coil. The principles used in the construction of a single-phase AC generator are also employed in 2- and 3-phase AC generators. The 3-phase system has 3 loops, set 120 degrees apart, 6 slip rings, and 3 outputs represented by these 3 voltmeters. The output, as shown here, will consist of 3 individual AC voltages, identical in amplitude and 120 electrical degrees out of phase. The 3-phase system has many practical applications and is widely used. Alternating current generators using electromagnetic fields, however, cannot be self-excited. DC is needed to excite the field. In practice, a small DC generator set in tandem with the main machine in one housing does this. Large AC generators are sometimes constructed with a stationary armature and a rotating field. Here, the coils of the armature are set around the circumference of the yoke. The poles of the field rotate within the armature to avoid the use of slip rings and to obtain direct connections to the load. Brushes and slip rings are used, however, to connect the AC generator to the outside low-voltage DC source needed to excite the field. Sparking brushes at low voltage does not represent a serious problem. Because AC has proven itself a versatile and practical type of power, many kinds of AC machinery are in use. To operate as a motor, an EMF must be generated in the conductor. We know that rotating a conductor through a magnetic field generates an EMF. The same effect can be accomplished by holding the conductor stationary and rotating the field instead. Lines of force are still being cut, and so an EMF is generated. Either the conductor or the field must remain stationary or move at a slower rate. That is to say, relative motion must always exist between the armature and the field in order to generate an EMF in the armature. We can construct an AC motor by closing the loop ends of the armature, thereby inducing a larger current in the loop and creating stronger magnetic fields around the conductors. This is a simple induction motor. The interaction between the conductor fields due to relative motion and the rotating magnetic field causes the rotor to move, but at a slower pace than the rotating field. If the speed of the rotor and the field were the same, there would be no induced EMF. No lines of force would be cut and no field built around the conductor. Obviously, there can be no motor action under those conditions. This, however, is an impossible situation. For if the rotor stops while the field continues to turn, relative motion will have been re-established. Lines of force are being cut once more. An EMF is generated and the resultant magnetic field will cause the rotor to move again. So far, we have rotated the field by physical means, which is impractical. It is necessary to find a way to rotate the field electrically. We saw earlier how 3 voltages 120 degrees out of phase were generated. This voltage can be used to rotate the field electrically. Six magnets set in a circular arrangement represent the field of a 3-phase induction motor. These 3 pairs of conductors, 1 pair for each AC phase, supply the field. Because of the time difference in the 3 phases, the poles will be energized in successive order, thus rotating the field electrically. Since the rotating field is cutting the rotor, it will rotate in the same direction as the rotating field, but at a slightly slower speed. Three-phase motors have special value in situations where it is important to maintain constant speeds under changing loads. Another type of AC motor is the two-phase induction motor, used especially where it is necessary to change direction of rotation quickly, such as in a radar antenna. The current used in this motor is two-phase AC. That is to say, two separate AC voltages 90 degrees out of phase. Just as in three-phase motors, the phase difference is used here to energize the field poles progressively, thus causing electrical rotation of the magnetic field. As in all induction motors, electrical rotation of the magnetic field is a primary objective. Again, the rotor turns in the same direction as the magnetic field, but at a slightly slower speed. The two-phase motor in this installation is called on to change its direction rapidly. This rapid change of direction is accomplished simply by reversing the polarity of only one set of poles in the motor. The polarity of the second set of poles will remain unreversed. The field will now rotate in the opposite direction, with the rotor following at a slightly slower speed. The most common type of current available in most sections of the country is single-phase AC. For that reason, single-phase induction motors are widely used for many and varied purposes. In the single-phase induction motor pictured here, the single AC output energizes both sets of poles simultaneously. There is no phase difference in this arrangement, and so the field will not rotate. As the cycle of the AC wave changes, the poles pulsate alternately. But since there is no relative motion, the rotor will not turn. The major problem is getting it started. If the rotor is started by hand, relative motion is created and the motor will continue to run. But this is not a very practical method. There are several ways to start a single-phase induction motor. One method is the use of shaded poles in the field. A shaded pole is attained by placing a copper ring in a slot over half the pole. The copper ring on the shaded half of the pole increases the inductance of that half. That causes the magnetic field of the shaded half of the pole face to lag behind that of the unshaded portion, creating a rotational effect. Lines of force will emerge from this unshaded section of the pole face first. The inductance caused by the ring makes the shaded portion of the pole lag behind. This alternating pulsating action creates a phase difference within the pole. Let us see now how the use of shaded poles actually produce a torque or turning force in a single-phase induction motor. The single-phase AC energizes the unshaded portions of the poles first and creates magnetic fields in these areas. The phase difference caused by the higher inductance of the shaded sections is responsible for the lag in the development of magnetic fields in them. As the current cycle changes, the same action will take place in all the poles. Relative motion, the basic requirement of an induction motor, has been satisfied. The rotor turns. Because of the relatively small phase difference developed by this method, shaded pole motors start slowly and are not used where a great deal of starting torque is required. There is another way to start the single-phase induction motor. In addition to the main poles, starting poles with separate windings are used. Phase difference is created by using high-resistance wires for the starting poles and low-resistance wires for the main poles. To understand the operation of the starter winding, it is necessary to bear in mind something of the character of the AC power supply. In any pure inductance, current lags behind voltage by 90 degrees. But since the heavy winding is not a pure inductance, but a large inductance, the current will lag the voltage in this winding by less than 90 degrees, say 80 degrees. The greater resistance of the starter winding, because of its smaller diameter, causes the current to lag the voltage by much less than 90 degrees, say 30 degrees. The net effect is then that the greater resistance of the starter windings causes the phase shift to be less than that of the main winding. We now have in effect a two-phase current. The phase difference causes the starter windings to be energized before the main windings. Magnetic fields are formed progressively. This is called a split-phase motor. The magnetic field now rotates electrically. The basic requirement of relative motion has been satisfied and the motor has been started. When the rotor has attained approximately 25% of its rated speed, a centrifugal switch opens and disconnects the starter windings. The phase shift accomplished by the addition of starter windings is not very great. The starting torque in this split-phase arrangement, although better than that in the shaded pole motor, is still not too good. A third method for starting single-phase induction motors is the use of starter windings with high-capacity electrolytic capacitors. We saw in our last example how a phase difference was developed by the use of starter windings. Now, when a capacitor is added in series with a starter winding, it offsets the inductance, causing an even greater phase shift between the two currents. This is a capacitor-start motor with a centrifugal switch. When the motor has attained 25% of its running speed, the centrifugal switch disconnects the starter windings. The centrifugal switch is mounted on the rotor shaft and is the type used on most split-phase motors. Since the greatest phase shift and relative motion is caused by the capacitor-start method, it is used in situations where good starting torque is an important consideration. Among the principal types of AC motors in use, the synchronous motor is used in situations where constant running speed is the governing factor. You'll remember that the operation of the induction motor depended on relative motion, that is, the difference in speed between the rotor and the rotating magnetic field. This relative motion induced an EMF in the rotor. In the synchronous motor, however, a different situation exists. Here, a multi-phase source of AC is applied to the stator windings, producing a rotating field, and a separate DC voltage is applied to the rotor windings, producing an independent magnetic field. There is no need for relative motion here. The synchronous motor is so designed that the rotor and the field rotate at the same speed. This is of importance when synchronous motors are used to drive equipment requiring this characteristic. Now to summarize, all rotating generators produce AC internally. The AC character of the output is maintained in the AC generator by the use of slip rings as load connectors. The frequency of the AC generator can be changed by introducing additional magnetic fields. The formula for frequency can be expressed as follows. F, or frequency in cycles per second, equals P, the number of poles, times N, revolutions per minute, over 120. The simplest AC generator shown here is the single-phase generator. This machine produces a single AC voltage. In the two-phase generator, we find two loops 90 degrees apart. And in the three-phase generator, three loops 120 degrees apart. The output of the three-phase generator, therefore, will be three AC voltages 120 degrees out of phase. The field of an AC generator is always excited by a DC voltage, in this case by a small DC generator in tandem. When it comes to AC motors, the most commonly used is the induction motor, whose basic operating principle is the electrical rotation of the magnetic field. Relative motion must be maintained. That is, the rotor must move at a slower pace than the rotating field. The three-phase induction motor is very efficient and widely used. The single-phase induction motor differs from the polyphase motors in that it is not self-starting. Since there is no phase difference in the single-phase current, the field pulsates instead of rotating. In order to create relative motion between field and rotor, shaded poles may be used. The unshaded portion is energized first. Because of the increased inductance in the shaded portion, the field here develops more slowly. Another method is the use of starter poles with high resistance windings. The high resistance in the starter winding causes the current to be out of phase with the current in the low resistance winding of the main pole. Magnetic fields are formed progressively and relative motion is begun. In the third method, a capacitor is placed in series with the starter winding. This causes a greater phase shift between the two windings. We now have two-phase operation on single-phase voltage. In synchronous motors, there is no need for relative motion. The EMF needed for the rotor is supplied from an outside DC source. Here, the rotor and the revolving field rotate at the same speed. AC rotating electrical equipment is the most practical for a multitude of uses. Knowledge of the principles of alternating current is essential to intelligent operation of such equipment.